Hi, welcome to Differential Equations. Today's topic is going to be Introduction to Modeling using ODEs. You see, I've written a long list of topics here. Let's just take a look at them. Finance and continuous compounding, population growth, spread of diseases, chemical reaction rates, mixing, draining, radioactive decay and carbon dating, Newton law of cooling, light absorption, free fall, escape velocity, and electrical circuits. You see that these topics range over just about any science classes a student might take in freshman or sophomore year. And one of the main selling points of ordinary differential equations is that all areas of science connect to this field. So if you take any of these science classes, more than likely you see a tie-in with differential equations or with statistics. These two are two major mathematical courses that dictate the behavior and growth of various systems. Now let's go ahead and see what's the reason for that, and then practice a few problems. Uh, all of these problems that you see here, one way or another, relate to differential equations of the type dy dx equals to ay plus b. First, we want to see where do these equations come from, how do they relate to these topics, and then later on we are going to learn how to solve them. Now the topics that we have here range from items that are familiar to everyone to items that are rather specialized. So for example, everybody has a bank account and they know about interest and accumulation of money in the account and so on. So pretty much everybody has a feel for what it is. As you come toward the end of it, the issue of electrical circuits and how these circuits behave, well, that requires physics 102, electromagnetism, and currents, capacitors, inductors, resistors, and so on and so forth. So that's probably a little bit more advanced than the rest of them. So we are going to concentrate on things that are probably familiar to everyone at this stage. Let's go to the very first one. How does finance and continuous compounding relate to differential equations? So we know that if you put money in an account, you are essentially lending that something that belongs to you to a bank, and then of course you expect to be paid something for this act. You're lending somebody money. So when you lend somebody some money, you get money back in one of two ways. Either a percentage of the money that you gave will be given as extra money back to you, or you buy a share of a company. So you either buy stocks or you put your money in a bank account. This is one of two standard ways people manage their finances. Now, these days the interest rates are rather low, so you might not be paying attention at all to interest that being accumulated to your account. But the other flip side of the coin, when you're using your credit card and you don't pay full amount at the end of the month, you do definitely pay a huge amount of interest for borrowing from somebody else. So one way or another, this issue is there. Now let's go. Let's take a beginning approach to this. Suppose you have $1,000 to your name, and you will put this thing in a bank, and you go and look far and wide, and hopefully you find a bank that gives you 5% interest. Well, what does 5% mean? 5% means that if you put your money in the account for 1 year, you get approximately $50. I said approximately because of some fine prints next to this. You get about $50 at the end of the year. How do I get 50? Well, 1,000 times 5% is 0.05, and then when you multiply it, you get 50. This is called simple interest. Simple interest, you take your money, multiply by the interest rate, you multiply by the length of time. So here I kept the money in the account for 1 year, and then I got $50. So if I keep it for 2 years, then I'm going to get $100 and so on. Now the important thing is that, well, if you had started with $2,000 under the same scenario, well, you get twice as much. That's not surprising. If I had started with $3,000 and the same interest rate, well, I would have gotten 3 times as much. This is the essence of the issue, that the extra amount that you get is proportional to how much you're starting with. So let's suppose S is a function of T, and this is your savings account. Savings account total. Well, you expect your account to accrue interest. So S is going to change in time because you lend your money to somebody and you hope that person is going to pay you some money back. So there is a DS. Differential of S refers to how much that S is going to change. We just said DS depends on how long you're going to leave the money in the account. Let's call that DT, elements of time. It's going to depend how much you had in your account to begin with, so that's called S. And going to depend on something we call interest rate, which we are going to hold fixed. It's some number. We are going to have this decimal number in mind, RDT. So the change in the account is proportional to what the interest rate is, well, how much money you got in your account, and what the length of time it is you leave it on the account. So the issue of continuous compounding refers to the situation that you leave your money in an account for a little bit, your account grows, and then you go back to the bank and say, look, my money has grown, and now I want you to use my latest total for calculating the next interest that you're going to pay me. So that's the issue of continuous compounding, as opposed to waiting an entire month or an entire year to collect your interest. You continually collect your interest. At any rate, ds is r ds dt. Another way of writing is that ds over dt is r times s. Now you might not be familiar with this kind of lettering. If instead of y, instead of s, I had used the generic letter y, instead of t, I had used letter x. You're so much in love with. And r, let me just use some number. Let me just use some easy number so that we don't go into after decimal numbers and such. Let's suppose this is 2. And then, well, we said instead of s, we are using y. So dy dx is 2y. No, so we translated from this meaningful set of letters that was savings account, time, interest rate. We wrote it in a generically mathematical way where none of the letters mean anything. Okay, now come back to the following issue. What's a function whose derivative is twice itself? What's a function whose derivative is twice itself? You want to pause for a second, rummage in your head for the formulas from calculus 1. So what was that function? Who was it that when I differentiated, it just as if it doubled? Common mistake here is to say x squared, because the derivative of x squared has a 2 in it. But notice it's not 2x squared, it's 2x. That doesn't do it, is that right? This is not what we want. What do we want? We want exponential of 2x. When you differentiate it, a factor of 2 comes in and becomes 2 exponential of 2x. So that's the issue of how to solve it. We are going to come back to that issue later on. Just this is a preview of things to come. But what I want to get at is, where does this equation come from? We said this is all these topics connect to this type of equation, that the derivative, if some multiple of the function itself and perhaps plus a certain amount. Well, where does b come from? Most of the questions in section 1.3 is asking you to think about the scenarios where these things show up and what their influence would be. For example, in this case, in the case of finance, where do you think b is going to come from? Well, very easy. If you are putting money into your account, well, at the beginning you put some money and it grows, but every now and then perhaps you go and put an additional deposit, and this b plays the role of that deposit, except that perhaps you go and deposit money once a month or once every year or something. But here in differential equation, we make things very easy so that our mathematics will be simple. We are going to assume this is your rate of continuous deposit. This is the money that you want to put in your account at the end of the month. Chop it off and go to the bank every day, as if you had nothing better to do. Go there, put a little bit of money. At every moment you're putting a little bit of money. So that is the rate at which you are saving money and adding to your savings account. So if I had something like that, I would perhaps will have ds dt, and then if my rate of interest was 5%, it's going to 0.05s. And then if per unit of time I am adding an extra, say, $100 to my account, that's going to be the differential equation that reflects my interest rate, my deposit per unit of time, and then all of these problems have a starting scenario. We call it initial condition. We call it S of 0. S of 0 means how are you going to open that account? Are you going to open with 1,000, 2,000, 3,000? So S sub 0, for example, could be $1,000 or $2,000 something. So this differential equation is capturing a bank account with a certain specification, a rate of deposit, initial amount, and so on. That's the story with pretty much all of these. And we are going to take a look at several problems. For example, population growth follows very closely the issue of continuous compounding. Population is like money in the bank. Just money grows, so does the population. And then you will have just a change of lettering. Here we have the S. Perhaps now we use P for population. Time, well, time is always time. And then we have rate of growth of the population. Like on average, typical society, has a growth rate of 2%. But of course, different societies are very different. You go far east, they are actually losing population. Here, maybe 2%, 1.5%, and so on. More affluent regions, somehow people don't have kids. Less affluent, they have more kids, and so on. All sorts of social and cultural issues influence what this number is, but whatever it is, so 0.02 P now, we say growth in the population is proportional to the population. That makes very good sense, because more people you have, more babies you have. more people you have, more people die. So birth rate minus growth rate becomes your population growth rate. And it is some number, typically constant for a while. In there, that becomes that equation. Now, how about this B? What would be the role of that? What scenario would you think you will add something to it or perhaps subtract something from it? It's one of the first problems you have. Of course, if you have people coming into the society, immigrating into or immigrating out of it, then you're going to either have additional population coming in, just like going to the bank and putting more money there, or perhaps going to the bank and withdrawing some money out of there. So if you put more, you add. If you take a withdrawal, you subtract. Same way with population. If you add, then, well, you add. If the population is leaving, then perhaps you subtract. So whatever this number is, again, for the sake of simplicity, we keep it a constant so that our equations wouldn't become too complicated for us to solve. Of course, in real life scenarios, these numbers also change with time and make the problem a lot harder. So continuous compounding is very easy to justify how it connects to differential equation. Population growth, same way. Spread of disease. Okay, well, we have been dealing with that. You can see many articles related to how COVID spread and how people were trying to solve equation that will predict how it's going to spread. But suppose we have a situation that people are not taking any precautions at all. The interactions are all totally random. There is no quarantine, nothing. So you have a sick population and you have a healthy population. So sick so let's S to be a number of sick people. So previously S was our money, now S is how many people are sick. So ds dt will represent how that population is going to change. Well, now it comes a lot of issue of biology and complication of how diseases spread and so on. So it's not as easy as money or things that are very clear cut. When we come to biology, we always have to take these things with a grain of salt. It's like a lot of simplification involved in converting biology to mathematics, but the essence of it is still true. The sick people are going to make healthy people also sick. So we have a total population. Suppose we have a total population out of which S is sick, and then T minus S will be then healthy people. Now sick people are going to randomly meet healthy people and make them sick. Well, how often do these two meet each other? Well, that comes an act of modeling. We say the more sick people we have, the more encounters we have. The more healthy people we have, the more encounters we have. If I multiply the two of them, that represents how often they meet each other. Okay, then I need some sort of a constant that tells me the transmission rate. At what rate are these people making those people sick? So I'll have some transmission rate, some small number, perhaps 0.1, 0.01 or something. So S grows based on an equation like that. Of course, in absence of any precautions, everybody going out and doing whatever they want and randomly meeting between sick people and healthy people. Suppose an innocent cold. You're not taking any precautions, you're going to games and so on, and things happen. So that is how spread of diseases can be model. Our equation is not like this, a bit more complicated. We are going to see those type of equations later on in the context of population growth as well. Chemical reactions, also when you have components in a container reacting with each other and creating new chemicals, well, you want to study at what rate does this happen, and as the chemical reaction happens, the amount of certain substances that are making that reaction is reducing at the expense of new chemicals being produced. So that can be captured in a differential equation as well. However, it requires a little bit of background in chemistry, and so I'm not going to get into that. We are going to go after topics that are very familiar to everyone or can be easily justified. Issue of mixing, for example, is a topic that is that doesn't require any background. So what is mixing issue? Here we have some container, a tank or something, and the tank has some liquid, perhaps water, which has certain amount of salt in it, and then we bring another pipe into the tank where it brings in more water at a certain salinity. So more salt is coming with more water into the tank, and perhaps we let some water to leave the tank. So we have water and salt here, and water and salts coming in, and we mix the solution. So that's why it's called mixing problem. And let the water out at a certain rate. We let the water in, at a certain rate we let the water go out, and then we ask ourselves the following question: what happens to the amount of salt that is in the tank? What happens to the concentration? Does it go up? Does it go down? At what rate? And so on. So that's a type of problem that we're also going to take a look at. Draining problem. Draining problem is just the mechanics of draining a tub. So suppose we have a tub, we make a hole in it, and then we let the water come out. That's all. How does that relate to differential equation? Well, there are laws that govern at what rate the water leaves the tank. Okay, of course, as the height drops, you are going to have a slower rate leaving the tank. So what we want to know, for example, is the height of the water as a function of time. What happens to the height of water? How does that relate to this hole at the bottom of the tank, and so on. Radioactive decay problem, of course, carbon dating problem, very similar to finance problems, but in this case, instead of finance problem where money was producing more money, we have the opposite of that. A substance decays, and as a result of that, the amount of that substance reduces. So that's going to have an equation very similar to this, except that the rate that we have is going to be negative. Then we have these other ones, Newton's law of cooling, a little bit more sophisticated version of some of these problems. Light absorption, very similar to radioactive decay. Free fall, you see this thing in your physics classes quite a bit. Escape velocity is a little bit more complicated version of this mechanical problem. And we said we are going to put electrical circuits for another class. Now let's go ahead and take a look at a few problems. So first one, it says a large mixing tank holds 200 gallons of water in which 20 pounds of salt has been dissolved. So what does that mean? It's just we have a tank. It starts with 200, it has 200 gallons of water in it. And to begin with, we have dumped 20 pounds of salt into this. Now pure water is pumped into the tank, so for whatever reason we are bringing water, and this one doesn't have any salt in it. That makes it a lot easier. So this is pure water coming in. Well, at what rate? So it tells us at the rate of 2 gallons per minute. So some hose is coming in, and the solution is well stirred. So we have some mixer here that is mixing this thing quickly, so it's not like up here is pure water and down here is salty water. No, it's being quickly mixed. The solution is well stirred. It is then pumped out at the same rate. So this is important. It says same rate. So same rate means, well, 2 gallons per minute. Why is that significant? Well, if I pump out at a lower rate, what happens? If it's 1 gallon per minute I take out, of course the water starts to rise. If I pump out quickly, say 3 gallons per minute, well, that's essentially draining the tank. So more advanced problems, these things could be higher or lower or variable and so on, and makes the problem more interesting. But right now, to keep it simple, 2 gallons per minute is coming in, 2 gallons per minute is leaving. So the level stays steady. So what is that we want? Determine a differential equation for the amount of salt. So we are after A of t. So we have a cast of characters. T is always time, and time set at 0 at the beginning of our experiment. A of t is the amount of salt. So we have to be clear for ourselves, what do we mean by amount of salt? Well, let's make it like this. What's the total amount in pounds in the container? We could have asked about concentration, we could have asked about all sorts of things. Here, amount of salt, we mean total amount of salt in the tank in pounds. So of course, at time 0, when we start this whole thing, how much salt do we have? Well, we have 20, so that's easy. What's the question? The question is, how does it change? What is the rate of change of A per unit of time? Our time is of course measured in minutes. So what do you think? Again, you want to pause for a second and try to come up with a reasoning yourself as to what do you think is happening here.